Hello, hello, and welcome everyone to the 5th day of our C tutorial series. I hope that everyone's having a good day. I see that we've got some of our repeat viewers in the chat. Blue Jay, TTV, have this. Olivia, how are y'all doing? My day's been pretty good so far. Hey, Prince Logic, welcome back. Welcome back. Happy to see everyone here today. Yeah, hola, hola. Yo no hablo español, believe it or not. I live in Texas, but I studied Latin for 6 years, not Spanish. So, posso lo que latine sed no lingua hispanico. But anyway, yeah, so today we're actually going to be doing something that's a little bit different from what we've done in the past. The past few days, we have been talking about some very kind of foundational concepts in C. We've talked about basic data types, we've talked about pointers, we've talked about arrays and strings, and yesterday we kind of wrapped all that together with talking about structs. And today we're going to be diving into how we can combine all of that together to write our own library in C. And Blue Jay, you studied Spanish for 4 years and still barely understand it. That's fair. Yeah, that's fair. A lot of language programs seem to not do a very good job of teaching, like, discourse. And so, yeah, I know a lot of people who took lots of language classes and can't speak it. Interestingly, we did no speaking, but I can kind of sort of speak Latin okay. So at least I got that going for me. But anyway, yeah, let's dive right into this. So, yeah, today we're going to be live coding a library, and the type of library that I would like to write is an emulation of Java's ArrayList. So ArrayList in Java, for anyone who's watching and isn't fully familiar, is a dynamically growing list. It's a dynamically sized list. And actually here, I'll show you how ArrayList works here using the Java REPL. So, for anyone who isn't too familiar... Oh, this is the wrong shell, isn't it? Yes, it is. Java actually builds in a REPL, a read, eval, print, loop environment called JShell that we can use to just kind of type commands and evaluate things without having to write an entire program and a class and all that stuff. We can just type single statements and they will run. So let's go ahead and import java.util.ArrayList. There we go. And so let's say I just want to make an array list of integer called test. New array list. Let's make sure I can still write Java after doing C for a week. There we go. Okay, so yeah, array list is this kind of dynamically grown list. If we start off, we see that the size of this list is 0. We have no elements. And we can, of course, add elements to this list. So I can add 4, 3, and 7. And then print my list. You can insert elements. So let's insert 5 at index 1. Oh, we don't have a method called insert. It's just add. I think it's an overload of add, isn't it? Oh, it's index first. Add 1, 5. Yeah, I don't work with Java ArrayList too much, but there we go. Yeah, so that's how ArrayList works in Java. And today, we are going to be writing kind of our own version of this in C. Oh, and yeah, a lot of people seem not to know about this. It is kind of a new feature, but yeah, it's the JShell REPL environment built into at least newer versions of the OpenJDK, which is what I'm running here. So yeah, totally, if you're going to be writing Java, give it a try. It's oftentimes pretty useful for just determining what a method might do, or just evaluating single lines. You can even use it as a calculator if you want, but I think Python kind of makes a better calculator. But anyway, yeah, so that's ArrayList, and we're going to be writing a version of this today in C. And now, the version that we are going to be writing is not going to be called ArrayList, I'm going to call it vector. And the reason I'm calling it vector is very simply because that is what C++ calls it, and I know that if I'm writing C and I keep making myself try and type ArrayList, I'm going to mess it up every single time. So yeah, we're going to go with vector instead, because I have a higher chance of typing that correctly. Also because that is a fairly common name across languages for that kind of dynamically sized list data type. Rust calls it vec, and Python is just a list. But yeah, C++ vector, and we're going to call it a vector here too. So yeah, let's just dive into this of how we're actually going to structure our library. So what we're going to do here is we are going to write this library in a test-driven style. So what that means is that every time we are trying to add a feature, we are going to write unit tests. And so yeah, so we're going to be doing some test-driven development today, TDD, get in all of our buzzwords just because we can. And part of the reason that I'm doing this is to show you how to use a unit testing library that I'm going to use when I release the linked list assignment that I'm going to give to everyone on the stream in a few days. And so this is just kind of to get you used to that library that we're going to be using for our unit testing. And so yeah, so the way that we are going to structure our project is that I am going to put most of our vector code inside of a file called vector.c. So yeah, so that's going to be where the majority of our vector code is going to live. And so yeah, so that's where all the actual functional code is going to go. And then also, to declare the public interface, we are going to be writing a header file. So yeah, so today is the day that we learn about header files. And let's just go ahead and jump right into what is a header file. So in C, a header file is really just a file that ends in the extension .h. So that is a header file, and I apologize for the background noise. I'm not really sure what that is. The person in the apartment above me may be vacuuming. Apologies. But anyway, yeah, so a header file is where we declare the public interface of our project or of our module. And so here's where we're going to put things like method declarations, method declarations, definitions. So where we actually write kind of the header of our method, right? The type signature, the name, all of that. It's oftentimes where we're going to put data type definitions that we want to be public. So any struct definitions we have that we want to be accessible outside of our module, directly outside of our C file, we're also going to put in the header file. And so to write a header file, what we're typically going to do is, before we even start writing the code, we're actually going to begin with this kind of magic incantation that we called an include guard. Now, what an include guard does, is it ensures that the structures in this file are only instantiated a single time. And so in C, every time we write hash include, like we might, hash include stdio.h, what this directive really does, this hash include directive, is it just goes to the file stdio.h, grabs all of the text, copies it, and pastes it into our file. That's all hash include does. It actually just grabs a file and it pastes it directly into our code. There's nothing more kind of advanced about it than that. It's really just fancy copy-paste, along with some name resolution. And so yeah, and so that's what hash include does. And so what happens is, if we hash include a file multiple times, and that file attempts to instantiate some data structures, what we can accidentally do is instantiate those data structures multiple times. And so, if I had in here, a definition of some, some data structure, int, static int x equals 7 or something like that, then this would be very simple. But every time we hash include this file, we're going to redeclare this integer x. If this were instead an integer array that contained, something like 50,000 elements, then this would start to become a significant problem. Right, this would become quite the issue because we would be reusing that memory every single time. We would be repasting the contents of this file into every file, which makes your compile time slower. And so, yeah, we don't want to do that. We don't want to keep reinstantiating everything that we need for our code. So we're going to use an include guard. And an include guard works like this. We start off by writing hash if ndef, which is short for if not defined, and then the name of our guard. Now, the way that I name my include guards is I typically type the name of the project. So this is our project name, C for Java programmers. And then the name of the header file, included. So this is a symbol that we are going to define that says, if this symbol is defined, then we are not going to try and reinstantiate the data structures in this file. And then after this, we're going to hash define this same symbol name. And then at the end of our file, we're going to have an end if to say we're going to end this statement if in def. And so these are some new preprocessor directives for us. We haven't seen these directives before. But in essence, what's happening here is we're going to try and import this file, and we're going to encounter this if end def. And what this says is, so if this symbol is defined, then we're going to skip to the end if. And this is actually going to be where our file ends, at this end if. And if it's not defined yet, then we're going to define the symbol and then, run all of the rest of our header. And so what's really happening here is we're saying we only want to potentially evaluate the code inside of this header file, inside of this if in def end if block one time. And so that's why we define our symbol in here. And so, so this is called an include guard. We're actually going to put these in, well, pretty much every C header file we write. We have to put these to ensure, again, that we don't get any unexpected behavior from just how the preprocessor includes files. So that's how we are going to, that's what we're just going to put that at the top of every header file. Every header file we write is going to have an include guard. And so the next thing we're going to do is start declaring the public interface of our module. And so this is going to be very straightforward. We're just going to think about, well, okay, what needs to go in an array list, right? What needs to go inside of a vector? And now I am going to start today by making a really big assumption about our vector. And we're going to change this later. I'll show you how we can change this. But we're going to start off by assuming that our vector is only going to store integers. Okay, so we've got a dynamically growing list of integers. We'll get to dynamic types later, because that requires some special techniques in C to get working. But we're going to start off by just having a list of integers. And so let's go ahead and define our data type. So the first thing we're going to do is declare our struct vector, right? So this is our actual vector data type. This is equivalent to writing, our class array list in Java. And so now we need to figure out, well, what members does a vector need? What data do we need to store inside of our vector? Well, let's think about it. Okay, so I know that a vector or an array list or whatever, dynamic list type this is, we had to have a size in Java, right? We had to have a size because we said that there may be extra capacity at the end of our array, just to ensure that when we add elements, it's going to be amortized constant time. Because most of the time when we add elements, all we've got to do is insert a value. We don't actually have to grow our list. We don't have to resize anything. We don't have to allocate any new memory. All we've got to do is set the element at the end of the current list to the element that we're trying to insert. And so what I'm going to do is I'm just going to write int capacity. And now, there are many different ideologies as to what types sizes should be in C. I had someone yesterday ask a question about a type that they had seen called size_t, like this. And size_t is a type that's kind of implementation specific. It's usually defined in the header stddef.h. And what size.t really denotes is the return type of the size of directive. So, the other day when we were writing things like size of int to determine how many bytes an integer took up, size of t just denotes the number of, the number of bytes that can be in a C data structure. And what this means is that it can actually be a proxy for the number of elements in an array. And you'll find many arguments as to whether or not you should use size t for this purpose. It's not the intended purpose, but if you use a little bit of logic following from the spec, then it does actually kind of make sense why we might use size of t for this. And so today, just to show off some alternative data types in C, and just to make sure that our code is maximally portable, because size of t is implementation defined, it'll depend on how much memory your system supports. We'll go ahead and use size of t here, just to make sure that our array is portable. I'm sorry, this is the capacity, this is the size, the number of elements in our list. So this is, and here we'll even document this. In C, we're going to document code just like in Java. In C, we use a tool called Doxygen to generate the documents. Sorry. Java uses JavaDoc, and the syntax is roughly the same between the two. Doxygen supports JavaDoc style comments, so we can just write documentation the same way as we did in Java. And so yeah, so this is the number of elements stored in our vector. And in Java, we also needed an array of integers, right? We needed an array of the values that we were storing in our vector. So I can just write, int, and we would usually call this in Java something like container, which is a tradition that we'll stick with here. And so yeah, so we had an array of integers to store our actual values. And now you could write this one of two ways. You could either write int con array, or you could write int pointer con. There's not an incredible amount of difference between the two. There's really not. If you write it using our array syntax, then you are essentially declaring that, the purpose of this pointer, right? Since arrays are just pointers to contiguous regions of memory, the purpose of this pointer is to point to an integer array. However, I like to be very explicit in my typing. I like to say exactly what things are and the purpose that they are used for. And I don't like to make kind of abstractions like that in my code. I don't like to say, well, yeah, I mean, this is technically an array, but really this is a pointer. And for our vector, it's going to be a pointer to dynamic memory. It's not an array of a fixed size. It's a pointer that we might be resizing. And so I am going to declare this as a pointer, and this is the actual elements in the vector as an array. And in Java, we could just get away with this, right? We could totally get away with just writing this, and it would work great. Because if we wanted to get the number of elements inside of this container, it was super duper easy. All we had to do was write con.length. However, remember that in C, arrays do not store their size. Arrays in C do not tell you how large they are, and so as a result, if we call size of con, we're going to see what we saw the other day, where we're going to call that, and we're going to see that it's going to return a constant 8 bytes, because that is how many bytes are in a pointer on my machine. And so we don't want to actually just call size of con. We want to store the number of elements that we can store in con. In other words, we want to store the capacity of our list, the maximum number of elements that we can store in it. So this is the maximum number of elements we can store. And if you remember, if you've been through a class in which you wrote a dynamically growing list, I'm assuming that most people here who have been through a data structures class, who have a CS education, have probably seen this before. Then you know that what's going to happen is when our size of our vector reaches the capacity, we're going to resize our array so that we can get some more space to add more elements. But we're not going to worry about that for right now. And so yeah, so here's vector.h, and you can see that this doesn't contain any code yet, right? We haven't actually written any code. All we have done is define our data type, which is one of the big things that we're going to do in our header files. We're defining the data types that other classes can use. Yeah, and someone says, yeah, the intless days of 3.14. Yeah, CS 3.14 is our data structures class at UT. And yeah, I'm basically actually kind of cribbing off a lecture from that class here, where we started off by writing our own dynamically growing list of integers, and then we moved on to a generic list. C doesn't have generics, so we're going to have to do that one a different way, and so you'll see how that's going to work. But yeah, this is kind of like the int list class that we wrote in Java. You're exactly right, Prince Logic. But anyway, so yeah, so here's our vector. And now you can see that if we make a new C file, and I'm going to call this vector.c, and I'll explain what we'll use this file for in just a sec, but if we hash include vector.h now, and I just start to write struct vector, you'll see that we now have the full definition of vector pulled into this file. So I can write, v dot, well, this needs to be inside something, so I'll just say, we'll just very briefly give it a function. So I say, struct vector v. You'll say v dot size, v dot capacity, etc. And so by including our header file in which we defined our struct, we've pulled in the definition of the struct to any file that requests it. And now, as a brief aside, someone asked me about this a few days ago, and I realized that I actually forgot to answer the question because we just kind of ran out of time, and I had kind of forgotten about it. And someone asked me, so I've seen in the past in C where people won't really define their vectors like this. They'll write something else. They'll write something like typedef struct vector sub t. And then they said, I actually really like doing this typedef thing, because what the typedef allows us to do is instead of writing struct vector everywhere, it lets us write vector sub t. And so we can instead of writing that struct keyword everywhere, just write our type name. And a lot of people actually really like that. However, there are some significant downsides to doing this. The first one, and the biggest one, is that it makes your code more difficult to read. Because not only do people now need to know about the actual structures that you have defined, they also need to know about your special typedefs. Typedef is just a way to alias a type in C. And so if I wanted to say, let's say that I wanted to rename unsigned long long to U64. I could just write typedef unsigned long long U64. And I now have a type called U64 that's alias to unsigned long long that I can use to, write values. And I can use that throughout my program. So that's the use of typedef. It just defines an alias for a C type. And this can sometimes be really useful when you're doing things like, writing, trying to write reusable code like you would see in a header file like stdint.h. If we go to stdint.h and we go to the definition of our types, then you'll see that all of these types that we talked about the other day, our int ble sub t types, are defined using typedefs. And that is actually super duper useful, but in typical usage, we actually don't want to typedef too many things. And the reason for that is that in general, we want to leave typedefs to the standard library. We want to allow the standard library to define its own types, but in general, we as library authors actually want to stick to just writing structs. We want to stick to the native syntax of the C language because it makes it easier for users to use our libraries. They don't have to know our typedefs, and they can determine what is part of our library and what is part of the standard library. Because our library will require struct, and the standard library will not. It will define these sub t types. The other aspect of typedefs is that people often do it wrong. So let's go back to where we said typedef struct vector sub t. This is actually a naming anti-pattern. This isn't something that we want to do, because in C, any type that ends in sub t is reserved for use by the standard library. And so a lot of C programmers are actually muddying the waters even more. They're saying, I'm going to declare a type, it's going to be called vector sub t, and I'm also just, by the way, going to use this naming convention that we've really reserved for the standard library just because I saw it and I think it looks cool. Right? All the other types end in sub t, which is true because the other ones you've seen are part of the standard library. And so for those reasons, I actually don't usually typedef any of my structs. I like to stick with just the struct keyword. It makes your code easier to read, makes it easier to parse. It ensures that people don't have to know your 8 bajillion typedefs you've got everywhere, and it ensures that you don't trample on the standard library. Because if you use a typedef with the suffix _t, future versions of the standard library might also use that name. Remember, the _t namespace is reserved for the standard library. So if the authors of the C standard library in a future version of the language decided, hey, I want a type called vector, and they called it vector sub t, your code is now broken because you trampled on their namespace that they did not want you to use. They said, we've reserved _t, and so you should not name anything that you're writing with that suffix. And so yeah, that's why we are going to stick with struct here. And Prince Logic, yeah, you've seen many competitive programmers alias long as LL. That doesn't surprise me. Competitive programmers are known for solving problems really quickly. And I admire how quickly they are able to solve problems. However, code quality is typically not a concern. And so, yeah, you see type names like LL, UL. Like, I've seen competitive programmers write code with variable names like XFPQ, which meant something to them, but not to any other human being who's alive. So yeah, we're going to today be imitating a more maintainable programming style. Something that you might see in production libraries. That will be a little bit easier for other people to work on. Cybergaming, missed the beginning, but what's size sub t? Right, yeah, so size sub t is from the standard library. It's from the header std_def, and it is a type that denotes, well, it's a type that can store basically the maximum size of something that you can allocate on your machine. It's really defined in the standard as the type that is returned from the size of directive that we've seen in the past few days. But we're using it here to indicate the maximum size of an array purely because we know that size of can return all of the sizes of an array if we declare it in local scope, and so it follows that size sub t can thus also be the size of an array in addition to just the type returned from size of. Yeah, so yeah, that's why we're using size sub t here. And so yeah, let's actually now get into writing our first vector function. So the first function that we are going to write is a function called vector create. And so this function is going to return a struct vector. We're going to call it vector create. And this function is going to take a single argument, a size sub t, denoting the initial capacity of our vector. And so here we are going to create a vector with initial capacity elements pre-allocated. And so, yeah, so here's where we're going to actually make a vector. And now you'll note that as we're going through this, I'm beginning all of my function names with vector underscore. And this is a really typical C programming convention, that we're going to start all of the names for functions in our module with the name of the module. So since this module is called vector, we're going to start all of our functions with vector. And the big reason for this is A, that in C, we don't have methods, right? So we can't just write, vector.method. That's not something that we can really do. We've got to get a little bit more creative. And so this is called namespacing. It's something that a lot of C programmers do just to indicate, hey, this function is part of my module. It says this function is part of the vector module. And so yeah, so we're saying this is a function in the vector module that will create a vector. And you'll see here that I haven't actually defined this function. I haven't actually given any code for this function. And the reason for that is that header files is not where you are going to write the actual definition of your function. It's where we're going to declare our function. We're going to declare the prototype. All right, so we're going to give it a return type and a name and some arguments, but we are not going to actually write the code here. Prince Logic, they're kind of like interfaces. I mean, at the most basic level, in terms of they define function, or they declare functions but don't define them, yes. But not really in any other way, because these functions are singletons. We can only have one function in our program called vector create. If we try and write multiple functions called vector create, then the compiler will throw an error. And so yeah, so we can't actually, do all the things we would with interfaces with these functions. It's really just a way of declaring the public interface of our module. So anything that you put inside of a header file is public, right? Anyone can go ahead and include this file into their C file, and they'll be able to access all of the things that we have declared here. And so, yeah, so it's really more like almost just writing the public keyword in front of things. It's essentially declaring, I got syntax highlighting for that for a second. That's interesting. But it's like declaring something public. It's saying it's externally accessible. In BlueJ, yeah, so this is where we are separating declaration and definition. Exactly. The declaration goes inside of our header file, and the definition is going to go inside of our C file. And so now, so I can get fancy autocomplete on this, let me go ahead and just add this to our CMake lists really quickly. It's going to contain vector.c. There we go. Reload our changes. Okay, great. So yeah, so now let's go ahead and write this function. And you'll notice that I've hash included vector.h at the top of this file. And the reason that I've done that is, well, basically because I need things like struct vector, right? I need all of the types that we have declared inside of vector.h. And moreover, since I am now defining the function that we declared in vector.h, I need to include that definition in this file so that the two can be linked together. And so that's why whenever we're writing the implementation for a header file, the implementation for a module in our C file, we're always going to include the header file as well, so we can get the types and the function prototypes. Prince Logic, when you're including a header file you made, does it have to be in the same folder? No, it actually doesn't. And actually, you could just type arbitrary paths here. And so, if this were in another directory, I could type, // something, right? To say it's in the upper directory. If I wanted to include something from another directory that's just outside of the path of this program, so like, I have a module called Pixels that I'm writing inside of this, project. And you see, we can hash include something that's in another directory completely. So yeah, they don't have to be in the same place. And now BlueJ asks another really, really good question, and that is, does it matter if we use the double quotes or the angle brackets in our includes? And it actually does. It has a little bit of a difference. So let's go ahead and write both forms just so you can see them here. So let's hash include. We're going to need stdio at some point because we're going to write a function to print our vector. So I'm just going to include stdio. Now, here's the difference between these two. stdio, you'll notice, we included using angle brackets, and vector we included using double quotes. The rule of thumb is, if you are including a header file that is in your project, in your local project, then you're going to use double quotes. Right, so if it's in the same project as the one you are working on, we're going to use double quotes. If it is not, we're going to use angle brackets. Now that's the usage. The way that these are actually defined is that if you use angle brackets, the C compiler is going to search your standard include path. And now, what is the include path? The include path is basically a list of directories that your C compiler has indexed in which it knows that it can look for header files. And so when we say hash include stdio.h, your compiler, and actually let me see if I can get our header path pulled up real quick. This will take like 1 second. Here we go. Right, yeah. So if we run GCC or any compiler with the -verbose option, --verbose, then you'll see it outputs all kinds of information up here, right? I mean, this is just all kinds of stuff. But as you scroll through this, you'll notice that as we go down, we see something that says hash include angle bracket search starts here. And it gives us this list of folders. And these are the folders in which your C compiler is looking for libraries, is looking for header files that we have included with angle brackets. So yeah, angle brackets for standard library or things that have been installed on your system. So if I do a directory listing of user/include, then you'll see we've got all these different header files for different modules, right? For different libraries that I may have installed on my system. And these are all things that I could just, hash include monetary.h, compile my program, and I would have all of the things that are in that interface. And so yeah, so that's the difference. But for now, when we're just working with vector.h, right, work with something in our local directory, we're going to stick with double quotes. Does that clarify things, Blue Jay? Yes. Okay, great. Good. Awesome. All right, cool. So now let's go ahead and write the definition of vector create. All right, now, vector create, we are going to use, we're trying to create a struct vector. And so what I'm going to do is I'm going to use our designated initializer syntax, where we're saying I'm going to return a struct. The type of this struct is going to be struct vector. And now all we've got to do is type our members. So the default capacity, well, actually, let's start with the default size. The default size is going to be 0. We're going to begin with no elements in our vector. The default capacity is going to be initial capacity. We've got a question from CyberGammy. Do you manually download these header libraries? Some of them. I mean, so the ones that are in the actual bona fide C standard library ship with your C compiler. So your C compiler will ship with these libraries. If I control click on this, then you'll see that this is the version that's shipped by Microsoft Visual C, right? Microsoft copyright header, and then all kinds of very bizarre Windows things that go along with it. Some of the ones from user include that we looked at a second ago, though, are from shared libraries that I have downloaded. So some of these are from the Unix standard library. So Unix, or POSIX, sorry, the POSIX standard library. So POSIX is a standard for operating systems that kind of builds on top of the C standard library. And so things in here like termios, syscall.h, strings.h aren't part of the C standard library, but they are part of the POSIX library. And so they come with most Unix systems. And then some of these are just other stuff that I've installed. Let me see if I can find... yeah, so here, GMP. GMP is the GNU multi-precision arithmetic library. It's used to do math on really, really big numbers. I've used it for some projects before, so I've installed it on my system. I installed it using apt, which is the Debian package manager. So yeah, so you can get these header files in different ways. Some of them are things that I have installed, some of them are things that came with my operating system, and some of them are C standard library functions that shipped with my compiler. So they come from all over the place. But anyway, back to writing our vector create function. And now the other thing I need to write here is my container. And now if I just try and write, int initial capacity, obviously that is not going to work, right? I mean, first off, just because that's not valid C syntax, but also because initial capacity is dynamically sized. But we know what to do with dynamically sized arrays now. When we need a dynamically sized amount of memory, all we've got to do is reach for our standard library, stdlib, and we're going to pull out malloc. So this array is going to be a container, and the size of this array, the size of this contiguous region of memory, is going to be the initial capacity times the size of an int, right? Because our vector is currently only storing ints, we are going to allocate the number of ints that were requested. Because if you'll recall, malloc takes a number of bytes to allocate. So yeah, so here if we request, let's say if we request 10 as our initial capacity, then we're going to end up allocating 10 times 4, or 40 bytes, which is exactly enough space in memory to store 10 integers. And so there is our vector create function. And Prince Logic, you mentioned you can't overload in C. Yeah, I can't overload in C. And so if I wanted to have a vector create that took a default capacity, I want to say, struct vector create. You can't do that. Your C compiler is going to tell you that you redefined the function, which it doesn't allow. So yeah, we don't have overloading in C. And there are workarounds for this. You can do all kinds of different stuff if you really wanted to. Typically, people just pick different names for their functions. And so, you know, this one, if we wanted to have a function that created a vector with a default capacity, then we might call that function something like vector create, the most common one. And then we would rename this to something like vector with capacity, something like that. And so, yeah, we might use different names for the things that we would use as, you know, quote, overloads in Java. But this is C. We don't have overloading, so we've got to stick with separate names. All right, just another restriction of C. C is a very simple language, and so C doesn't provide us with some of these nice kind of dynamic dispatch features that Java does. And so, yeah, so we're not going to get that here. Now let's go ahead and actually try and run some code, right? You've noticed that we haven't written a main function anywhere here, and the reason for that is that vector.c is not an entry point to our program. We don't want someone to just be able to run vector, right? Just like in Java, you couldn't run ArrayList because ArrayList didn't have a public static void main, string args, right? So we couldn't run the ArrayList class in Java, and we can't run vector in C because it does not include a main function. So let's go ahead and write something that does have a main function. And let's skip over to a new file that I've called test.c. Now, test.c right now is about as simple as it gets. It's literally a file that just returns exit success. We'll compile it just to make sure that things are working. And there we go. Finished with exit code 0, which is what exit success is defined to. So now we know that we are going to want to test vector here, right? This is a test of our vector class. And so I'm going to go ahead and hash include vector.h. And now that I've hash included vector.h, I can use all of the things that we have declared in the public interface of vector. And so this was our vector interface. Here's our test file. And so now what I can do is say, okay, well, I want to make a vector. So I'm going to say struct vector v equals vector create. Let's create it with a capacity of 10. Now, if I debug this program, and let's just say that I'm going to step over this line, then we'll see down here in the debugger, it's a little hard to see. I wonder if I can make this bigger. Yeah, I'm not going to try to make this bigger, but you can see that we've got a size of 0, a capacity of 10, and our container is an initialized pointer. So yeah, so we know that this is working. But, you know, this isn't really how I want to develop this library. As I said, we're going to be doing some test-driven development today. So we're going to be writing functions to test each of the operations that we're performing on our vector. And so I'm going to now hash include another library called test.h. And this is something that's in our local directory. And the reason it's in the local directory is because I wrote it. So yeah, so this is test.h. Test.h is kind of a pet project that I've had for a while. It's a single file unit testing framework for C. So you can see here it says it's a testing framework implemented entirely using the C preprocessor. And what this means is that the entire library is defined using preprocessor directives, and like a lot of them. And now the advantage of this library is that it lets us do some really cool things. The biggest one of those things is that it lets us run code without having to explicitly call functions. And so the main function for our program currently is just return exit success. It could actually be just nothing. And you'll remember that by default, a C program with no contents doesn't do anything. But now that we have included the test.h header, it's going to start auto-registering some functions. And so if I go over back to my left-hand screen here, and I now compile test.c, and note that I've also pulled in vector.c. I'm saying I want to compile both of these files to a binary. So whenever we're compiling a library that has multiple files, or a project that has multiple C files, we've got to list all of them in our cc command, just so that the C compiler knows to compile this file, vector.c, to find the definitions of our vector functions. I'm just going to call -o test. So the name of our output binary is test. And now if I run this binary, we've got some output. So this is all output from test.h. Test.h auto-registers some functions at start that do things like print a test report. And so now let's go ahead and write our first test. So in order to write a test using test.h, which, again, the reason that we're going through this is not so I can show off my fancy library, but because we're going to be using this for the linked list assignment that I put out, we need to start off by writing fixtures. And the way that we're going to do that is using some preprocessor directives, hash pragma fixture start and fixture end. And yeah, in Print's logic, yeah, this is because the fact, yeah, include actually just copy paste the file. And so test.h, what it does in short is it basically takes advantage of the fact that the executable formats that are used on Windows and Unix systems allow you to register functions that will run before main. It's very convoluted to do so. It's a really kind of odd roundabout process, but you can do it. You can actually register functions that run before main. And that's what this library does. And so the function that runs at the beginning of this program that you see that printed that report is a function called test kickoff, which you'll see has all kinds of strange annotations that basically are used to indicate when this function is going to run. And then down here, at least on Windows, we've got some code that registers the function to run on startup by placing it in a certain section of the executable that's compiled. It's a strange system, but it actually works. Windows 10 almost broke it, but I found a workaround. So thanks, Microsoft, for making my life harder last night. But anyway, yeah, so we can just run code on startup. Now, what I'm going to do is I'm going to declare a fixture. A fixture is basically a family of tests that all use the same data. And so each test has some data associated with it that can be used to do things like, store state, right? Or to maybe set up some common variables that we want to use in all of the tests in that family. And so I'm going to start by declaring a fixture, and I'm just going to call this fixture, let's just call it vector fixture. And now the way that fixtures work here is they're really just structs. And so if I want to have a struct vector in my fixture, all I've got to do is declare a struct vector inside of my fixture. And you'll see here that if I give you the full screen view so that you can actually see the little documentation hovers, you can see that this is indeed the vector that we made. It contains our documentation comment in vector.h. And if we hover over this macro, then you'll see that what this actually does, after an incredible amount of ceremony to do things like register functions and whatnot, is it's really just a struct declaration that auto-runs some code. So yeah, the C preprocessor. We might talk about the preprocessor. I'm actually kind of reluctant to, because people do weird things with the C preprocessor, and I'm afraid of what some of you may do with it, but we might talk about it. And now what I would like to do is at the beginning of every test in this family, I would actually like to construct a vector, right? I want to make a vector that we can use to run our tests. And so I'm going to write a function called fixture setup. And this says this is the function that's going to run before every single test that is in this fixture or in this test family. And all I'm going to do is I'm going to assign to vec the result of vector create with a capacity of 10. And T underscore, by the way, is just shorthand for saying test arrow, and test is a pointer to one of these structures. But yeah, I defined some shorthand just to make it easier to write. Okay, so great. So there's our fixture declaration, our fixture setup. And so now we can go ahead and write our first test. So let's do that. I'm going to clean this up a little bit. There we go. So our tests are delimited in a separate section of the file called test start and test end. And so let's go ahead and write our first test. The first test that we want to do is we want to determine whether our create function is actually working, right? We want to make sure that our tests are functioning correctly, or that our create function is functioning correctly. And so I'm going to write a test. I'm going to call it vector create works. The fixture is going to be vector fixture. And now within this test, I'm going to write a series of assertions. Assertions are just things that have to be true for the test to pass. If any assertion fails, then the test fails, and we know that something has gone wrong. So I'm going to do two things here. The first thing that I want to do is assert that the vector, or more specifically, the vector's container is non-null. And so I want to make sure that that vector's container is not null. Make sure that malloc actually returned a valid pointer. Because if it didn't, then obviously our test isn't going to work. But also, we just want to make sure that we actually properly allocated this vector. I also want to assert that the capacity of our vector is 10. And I want to assert that the size of our vector is 0. And now in some programming languages, people might say, hey, this is stupid. Why are you testing that the default values of variables are 0? Like, you don't need to test that in Java. You do in C, because if I forgot to initialize this variable, who knows what its value is? Right? Who knows what the value is going to be? And so now I can go ahead and run this program, and we'll see that if our create function is working properly, then we'll see a single test having passed. And there we go. We see that we've got our test called vector create works. It ran in obviously 0 seconds. It ran almost instantaneously, and the test passed. Awesome. Okay. So there we go. There is our nice function. And just to demo here, if you're on a Unix system, so the Windows console doesn't support color, but the Unix one does. And so, ignore that. We can actually go ahead and run... Oh, wait, this is a size of t, right? So actually, the format code for this should be ZU. There we go. Anyway, now that we'll switch back here, recompile our program. Yeah, be quiet. Those are just warnings about printf. You don't really need to worry about the printf code warnings too much. And we run this, then we'll see that our output has some pretty colors that describe to us what happens. If a test fails, which is something that you may see when you're debugging your own programs that you write that might use this library. So let's say that we're going to assert that the size is 1. Then you get a nice error message that says not only that an assertion failed, but also gives you the values and the location at which it occurred. So yeah, so this is how we're going to be testing our code today. We're going to be using this, this library called test.h that I wrote that gives us all of these nice features. So yeah, so let's go ahead and move on. Now, we know that we can now create a vector. That's great. Let's do some things with our vector. The next thing that we want to do is write another function. It's a void function called vector destroy. And vector destroy is going to take one argument. It's going to take a pointer to a vector. And now what vector destroy is going to do is it's going to deallocate the dynamic memory held by the vector. And so we're passing it a vector pointer. And you'll remember that within each vector, we have an integer pointer that we dynamically allocated on the stack. And if we forget to free all of these vectors, or all of these pointers, once we're done with our vectors, we're going to run into a memory leak, right? We're going to have malloc start to return null, and we're going to run out of memory. And so what this function is going to do is it's going to deallocate that dynamic memory. And so here's my function. And all we're going to do here is I'm going to call free on the vector's container. Right? That's all we've got to do is call free on this vector's container to say, hey, we're no longer using this memory, we can deallocate it. And then now, just for safety, this is really just a sanity check. I'm going to set the vector's container to null. And the reason that I actually want to set this to null is that it makes it easier to detect bugs, right? So if we just free this memory and then we try and reference it in the future, we're going to get a seg fault because that memory was no longer allocated to us. Or we're not going to get a seg fault, but we'll get some type of error. But this will just be some random address, right? It'll still be the value returned from malloc. But if we set it to null, it's very apparent when you open your program in a debugger that, hey, you tried to dereference a null pointer, you probably tried to use a bit of memory after you freed it. And this is what's called a use after free error, and they're very, very common in C programming. And you've just got to be very vigilant about when you're allocating and deallocating memory so that you can avoid them. Okay, so here's our vector destroy function. And let's go ahead now and write a test for vector destroy. Well, actually, the first thing I'm going to do here is I'm going to declare a teardown function for this fixture so that we're going to automatically deallocate or destroy this vector every time that a test in this family has ended, because otherwise we are actually still leaking memory. And so I'm just going to call vector destroy on our vector. Right, and so here we've got to pass a pointer, so I'm saying I'm passing to vector destroy the address of the vector member within this test struct. Okay, great. So there you go, there's our teardown function. And now I'm going to go ahead and test teardown as well. There's not really a good way to do this in terms of, you know, that we might accidentally destroy the vector twice. But as far as I'm aware, there's actually no harm in trying to free a null pointer. So let's go ahead and just try this out. So we're going to say test vector destroy deallocates. It's in vector fixture. And all we want to do is we want to call vector destroy on the vector member within our test struct. And then we want to assert that that pointer, oh, I actually don't have assert null. Oh, I do have assert null. There we go. That pointer tvec.con is null. We want to make sure that our container was nulled out. Let's go ahead and run this now. There we go. And we see that both of our tests have passed, meaning that vector destroy is now also working. All right, now this was fairly boring. We've written our lifecycle functions, and these are really important when we're writing a C library, right? These are really important to avoid memory leaks, to make sure that we are freeing any dynamic memory that we allocated, to have these lifecycle functions. They really do serve a very good purpose in C. But we'd like to do something more fun now, right? We'd like to actually make this vector usable. So what we're going to do now is we are going to write an add function for our vector. So we're going to write void vector add. And we're going to pass it a vector pointer and the element that we want to add. And so we're going to add the specified value to the vector, to the end of the vector. There we go. There's vector add. So you'll notice that as Java programmers, you may see something that's kind of a common pattern that's emerging. And that is that when we're defining functions for this struct vector, we're oftentimes passing a pointer to a vector in the argument, as the first argument, rather, of these functions. And you'd be completely correct. That is a common pattern when we're writing these C libraries, is that we're kind of imitating methods in a way, that we're passing a pointer to our structure into the function. And this is actually how some programming languages implement methods, is they actually do this, where they will, when you write, vector.add, it desugars that call into something that looks a lot like this. However, in C, again, we have to be very explicit. And so we're going to need to explicitly pass pointers as we go. So yeah, let's go ahead and write vector add. So let's see here. And actually, before... Nah, it's okay. Yeah, we can go ahead and do vector add. So yeah, let's go ahead and write vector add. We're going to implement this, obviously, in vector.c, which is where we're writing our definitions, as opposed to our declarations in the header. And now, if you're a seasoned Java programmer, then you'll know that, well, what this function is really doing is just dumping something in an array. So I should be able to just write vec con at vec size equals the value we're going to add, and then I can increment the size. You're like, cool, that should be it. We're done now, right? Well, not quite. We're not quite done. And the reason that we're not quite done is that we may run out of size in our container. Right? Or we may run out of capacity, sorry, in our container. And so if vec size has reached the vector's capacity, then we know that we need to resize this container before we can add more elements. But this isn't a big deal at all. And the reason this is not a big deal is that yesterday we talked about a function in C that can basically resize an array, that can reallocate or grow a block of memory while keeping the initial values there. And that function that we are going to write, that we're going to call, is realloc. And so I'm going to say, okay, so if the vector's size is equal to the vector's capacity, then we need to grow our vector. And now we don't actually need to, in Java, we actually wrote a function to do the growth, and we don't really need to do that here, but I'm going to do it anyway to show you how we can write functions in an implementation file that aren't declared in our header file. And so I'm going to write a static function called vector resize, and it's just going to take a single vector argument. And now the reason that I have declared this this function static, as I mentioned yesterday, is that in C, static really means something akin to private in Java. Static means that whatever we have written, whatever we have declared, is not accessible outside of the current translation unit, which means the current header file and C file. So if we write this function vector resize in our C file, but we declare it as static, and we don't include it in our header file, then someone off in some other file, like test.c, can't try and resize our vector when they shouldn't. And so that's how we do a very, very limited form of functional encapsulation in C. Now, we've gotten a way to actually encapsulate struct members, right? We can't do that, and so people can just mangle our struct however they want still. There's nothing preventing them from doing that. But we can kind of hide some details of our program. We can hide functions like this resize function that we don't want people to be able to call. So yeah, let's go ahead and write vector resize now as a private static function inside of our implementation file. And this is going to be really, really, really simple. All I'm going to do is I'm going to say the vector's container is going to be the result of calling realloc. And now we've got to pass realloc the thing we want to reallocate, which is vector con, and then a size. Now, my students should be very, very, very well aware of how we are going to resize this vector, partially because we beat it into you on several exams, but also because we talked about algorithmic analysis, and we talked about how we can ensure that our addition function always remains amortized constant time. And the way that we're going to do that is by resizing our vector by a factor of 2. And so I'm going to say that the vector's container is now going to grow to the capacity of oh, and IntelliJ just almost froze on me. That would have been bad. And then we're going to actually add a little extra capacity at the end too. And the reason that we're multiplying by 2 is that as we add elements, the resizes that we're performing are going to become less and less and less frequent. So they're going to happen less frequently. And as a result, if they happen less frequently, then that means that the average runtime of our function is going to start going from this order n runtime that's incurred when we have to reallocate our array down to the constant time runtime that occurs when we just have to set a value. And so yeah, so that's why we're multiplying this factor by 2, or the capacity by 2, and then we're also adding 10 just to give us a little bit of extra space as well. It just helps with the runtime efficiency. And now something that I haven't done yet that we probably should is include our header assert.h and write a few assertions. And the assertions that we should write is first off that our vector is non-null, right? So we need to make sure that our vector isn't null that's being passed into our public functions. And then here for vector resize, I want to make sure that realloc has returned a valid value. And so what I'm going to do is I'm going to assert that vec_con is not equal to null as well, just to make sure that we can still use this vector once we've resized it. And then down here, if the size is equal to the capacity, then I'm going to call vector resize with my vector pointer. BlueJay, printf statements are read by C as right to left, but not math. Yeah, that's correct. Yeah, so not just printfs actually, but the order in which the arguments to a function are called is undefined. And so if you execute a function call that has 2 arguments, you don't know whether this argument is going to be executed and then this one, or whether it's going to be the other way around, where we execute this argument first and then this one. It's undefined behavior in the C standard. We don't know what's going to run first. And so yeah, we call that undefined behavior, which means that your program shouldn't rely on the evaluation order. And what it also means is that in general, you should not have data dependencies. You should not have, you should not require the value of a value that might change somewhere else in a function call in another function parameter. If you need to actually modify one of these parameters, you should do it out of line, outside of the function call, instead of in your function call. And math in C, though, yeah, math in C works pretty much the way you would expect. I mean, there are obviously kind of some more, operators, right? Like in standard math, we don't see things like, the left shift operator. But yeah, so the operator precedence rules are a little bit different, but for arithmetic, it works exactly the same. So yeah, it's your standard, PEMDAS, right? Parentheses, not exponents, but multiplication and division, and then addition and subtraction, read left to right. So yeah, so here we're going to do the vec capacity times 2, and then add 10 to it. So yeah, it works like standard math. So there's nothing to be afraid of here with C math. It's fairly straightforward. Okay, great. And now I've actually forgotten to do one more thing, and that is I forgot to set the new capacity of my vector. I've got to actually set the capacity. And so what I need to do now is I need to set the capacity to its new capacity, which is going to be vec capacity times 2 plus 10. And then here I can instead just pass vec capacity to avoid repeating this expression. So just, some kind of clean code stuff here. And there we go. Now we should have no issues. We've now got enough space in our vector to insert our element, so we can proceed to insert it as normal and increment the size. And you asked, how do you do exponents in C? Right. So exponentiation, you can do it in, there's a header file called math.h. Math.h. And the exponent function is called, I think it's called pow. Yeah, it's called pow. And so you can do, if you wanted to do 4 to the second power, then you do 4 raised to the 2. So yeah, exponents are a function in math.h. There's no, standard operator for them like there is in Python and Ruby, and I'm sure Fortran probably has one. But yeah, C does not. C does not have exponentiation as a standard function. So yeah, there we go. Now we can add things to our vector, which is pretty nifty. And now before I write a test for vector add, I've actually got to do one more thing, which is I need a function to get values out of my vector, right? It's all well and good to add things to the vector, and we can even do that. So I can say, you know, test vector add single element within my vector fixture. I can say, you know, vector add to my vector, let's say the value 4. But I don't have any way to make sure that that value is actually in the vector. Now, I could snoop on the size of the vector, right? And that's kind of useful. So I could say, okay, assert equal, you know, the vector's, the vector's size is equal to 1. All right, and that would work, and that test would presumably pass. But we can't actually get the value. And so I'm going to write one more function, which is very simply just a get function, a lot like we would have written in Java. So I'm going to write int vector get. And here's our vector. And then we're going to take in a size sub t as the index. So we're going to retrieve the element at the specified index in the vector. All right. This function, fairly straightforward. We don't even need to talk about it too much. All we're going to do is we're going to return the element at index in vector's container. And that's it, right? That's all we actually need to do. That's really all we need to do. Since array access in C, since array access is really just performing pointer arithmetic on this pointer, what this does is it says, I want to return the value that is index integers away from the start of the container. Right, and that's kind of exactly what we really wanted to do here. We just want to return that value. And now I'm also going to add an assertion, right? I want to make sure that my vector is not equal to null. And I also want to assert that the index is less than the vector's size. Right? Just want to make sure that we're not trying to access an invalid element inside of our vector. And so we're doing some defensive programming, right? We've added assertions to say, hey, you can't do that type of access. You can't access off the end of our vector. And so we're not going to permit it by using an assertion. And now what I can do is something that's substantially more useful. I can assert that the value at index 0 in our vector is equal to the thing that we inserted, which was 4. Oh, yeah, and we've got a great question from Prince Logic. Yeah, it's basically preconditions. And yeah, BlueJay said correctly, yeah, this is preconditions, exactly. In Java, we check preconditions with an if statement and then throwing an exception. And in C, we're going to check them even more simply. We're going to check them by just asserting that these things are true. And if they're false, right, so we'll go ahead and run this program just to show you that it works currently. But let's make an assertion fail. Let's say that we try and get the element at index 1 in our vector, which is not a valid index. Well, we're going to get an error. We're going to see assertion failed. And then very thankfully, the runtime is extremely nice to us and says the assertion that failed, the text of the assertion, the file that it happened in, and then the line number that the assertion was on. So it's a little bit like a backtrace. It's not a real backtrace. It doesn't tell you, you know, your entire call stack or anything like that, but it at least gives you a very basic indication of what went wrong. And I will note that these assertions that we're writing in here come from assert.h. They come from this assert header file. They are very different from the assertions that are defined by test, which are defined in test.h and print test failure messages if they're wrong. And so if the result of this call was incorrect, then we'll see something a little bit different. We'll see a failure message printed by test.h, not the C runtime. There we go. So we can add a single element. And, you know, I'd actually really like to add another test to make sure that we can add multiple elements. So let's go ahead and write that test. Let's just say I'm going to add 3 elements now. I'm going to add a 4, a 3, and a 7. The size at the end of this should be 3. And then we should have as our values 4, and then 3, and then 7. And let's just make sure that our test still passes. And it does. Lovely. All 4 tests passed. Great. Now let's test resize. Yeah, that's kind of an important one. Let's make sure that resizing this vector actually works. So if we exceed our capacity, what's going to happen? So what I'm going to do now is say vector add with resize in our vector fixture. And I'm just going to add 11 elements to this list. So I is less than 11, I plus plus. And I'm just going to say, okay, I want to vector add to the test vector I. And now at the end of this test, I want to make sure that our vector resized and that we can actually get a value out of it. So the size of our vector should now be 11. And the element at index 10 should be 10. Right, since we're just adding subsequent indices to our vector. All right, and let's just make sure that that test passes as well. Oh, and we've got a little bit of an issue. Okay, we've got an error. Okay, process finished with exit code blah, blah, blah. I believe, and don't quote me on this, I think that's a segmentation fault. So let me actually go in and check that really quick. Let's see here. I'm not familiar with the Windows error codes, so let's go ahead and just run this here. And what? All the tests pass. Okay, that's interesting. Actually, what's going on with that? What? Let's just try that again. Oh, and they all pass now. Okay. Okay. I'm actually not sure what happened there. I legitimately don't know why that program terminated after it was done. Huh. Okay. Well, that's really weird. Okay, let's do some live debugging. Windows exit code C1234374. Let's see here. So what is this exit code? Oh, heap corruption. Interesting. Okay, why on earth would that happen? Oh, right. Okay, right. I actually made a mistake. Which can happen sometimes. This is programming, of course. We make mistakes, and when live programming, we especially make mistakes. Inside of my realloc in vector.c, I forgot that I need to remember to multiply my capacity by the size of the thing that's inside of my array. Right? Realloc takes a number of bytes, not a number of elements. It doesn't know how big the elements are, and so I need to remember to multiply my capacity by the size of the elements. Right. Careless bug. Careless error. This should now run just fine. Yeah, and it does. Okay, cool. There we go. Vector add with resize is working. It's working. I'm going to presume that this is now working. Great. Cool. Okay, there we go. Done. Yeah, kind of felt something was off. Couldn't point at it. Yeah. I'm not sure whether or not that's a pun. If it is, it's a fairly good one. Yeah, with pointers and whatnot. So yeah, so we've got to remember that when we're calling malloc, realloc, that we have to specify the size of our data type. It's just a fact of the function. And a mistake that I have made, yeah, I've made that mistake before too. It happens. So, anyway, there we go. Now we have ensured that add and get are working. And at this point, we've got what looks like a pretty good portion of a vector library. Right? I mean, we can add things to our vector. That's cool. Let's write another function. And let's write a function that's going to allow us to stretch our brains a little bit and do some more interesting operations. I'm going to write a function called vector insert. It's going to take our vector, and it's going to take an index and a value. And what this is going to do is it's going to insert the specified element value at the specified index of our vector. This is a lot like the ArrayLists.add function when you specify two arguments. And so if we just call add on an array list, right, then it just appends things to the end. But I can also call add with two arguments. It's got an overload that will allow me to insert things at a specific index in the vector. Oh, hey, XIS said, welcome back. Welcome back. Today we're imitating ArrayList in C. We're writing a library. So yeah, so our insert function is going to be equivalent to this form of ArrayList.add. And since we don't have any overloading in C, we've got to just give it a different name. So yeah, so we're going to insert the specified value at the specified index in the vector. All right, let's go ahead and write it. Boom, vector.c. Okay. So let's think about how we actually want to do this. This one is actually a little bit more challenging to write. And the reason why this one is more challenging to write is that we not only now have to place a value, we also have to shift values around, right? We have to kind of put values in different places. And BlueJay suggests, can we make a new container that has the value and the position required? I mean, we could make a new container, yeah, but that's actually doing a lot of memory thrashing. The more frequently we try and allocate and deallocate things, the more likely you're going to end up with something called memory fragmentation, which is something that you would learn about if you took an operating systems class. But memory fragmentation is basically when we try and allocate lots of little small pieces of memory, and then we deallocate them. And that basically results in your memory map looking like Swiss cheese, that we've got all these little holes that we can put things in, but we don't have any big gaps. And so as a result, what can happen is you can run out of space to allocate larger structures, but you still have a ton of free memory lying around. It's just too small. At which point, something called memory compaction has to occur, which is basically when all your memory gets moved around, and this is something that we can't actually really do in C. We can't really do memory compaction in C. And so, yeah, it's pretty bad. You don't want memory fragmentation. You really don't. Swiss cheese, right, yeah. Yeah, in case anyone is hungry. It is about lunchtime, so yeah, maybe I'll have a grilled cheese. That actually sounds pretty good. Anyway, yeah, so let's go ahead and write our insert function. And we've got to remember, so yeah, I like the suggestion, BlueJay. That is a good suggestion. And we did that in Java, right? We actually did that. But what we're going to do instead is, yeah, and Raji got this, we're actually just going to shift the values that come after the index at which we want to insert, and then plonk the value in the proper index. So yeah, that's what we're going to do instead. And it's just a slightly simpler way of doing this. So let's go ahead and write this function. Now, we're actually going to need a resize again. We might need a resize if we don't have any space to add this vector, or to add this element. And I don't like having to repeat this if statement everywhere. And so I'm actually going to do a small refactor. This is now going to be a function called vector try resize, and it's just going to contain the if statement too. And so now I can just say vector try resize vec. So I don't actually have to explicitly check now. The function's just going to do it. And XISZ for insert, we need 2 pointers. One that checks if the current one is filled, and a second one to check the end of the list. Right, so currently this is actually just a list of integers is what we're working with right now. So we don't have like reference semantics going on. And the way that we're handling the end of the list is that we have a capacity instance variable so that we don't have to do pointer math to resize things and shift things and all of that. So yeah, we're just storing the number of elements that we've got in our container along with the container. So it's a little simpler. And the 2-pointer approach is a good way to do things. I see a lot of people do that. We're just going to choose not to do that today because it's a little beyond the scope of what we're trying to do. We're mostly just trying to show how we write larger projects in C and play with dynamic memory a little bit. So anyway, so yeah, the first thing I want to do is I want to make sure, well, okay, my vector can't be null, right? Assert vector is not equal to null. No null pointers. And now what we need to do is make sure that this index is valid. And now we are actually going to accept the end of the list, right? So the size of the list as an index, and that's just going to mean that we want to add the value at the end of the list. And so what we're going to do is I'm going to say that I want to assert that the index is less than or equal to the size of the vector. Okay, great. So now we need to try and resize our vector, just in case we need more capacity to insert our element. And so now we need to actually do the insertion. And this is kind of tricky. This is kind of tricky in C because in Java, we actually just loop through our array. And you can actually do that here too. You can just loop through the array if you want. My only opposition to that is that it's kind of slow, right? Just like looping through the array would be slow. Maybe there's a faster way to do this. And it turns out that there is. So we're going to include string.h into this vector file. And the reason that we're going to include string.h is that string.h doesn't just deal with character strings. It actually deals with any contiguous regions of memory. And so it has functions to copy strings and work with strings. And it has functions to work with just general memory as well. And those are the functions that we are going to use here. And so the function that we are going to use, now we need to shift elements after the index down. Right? That's our goal. Now we've got to shift those elements that are after the index down 1 position so that we can insert our new element. And the function that we are going to use to do that is a function called memmove. So memmove is a function from string.h, and what it does is it does what it sounds like. It moves a region of memory. And so if we want to move every element in this list from the specified index down a single position, well, then I'm going to say my destination, right? So my pointer to the destination, which is the first argument to memmove, is going to be vector container plus my index plus 1. Right, so we're saying, so the element that we want to move everything to is starting at the specified index, and then we want to advance it 1 position forward. Our source pointer is just going to be the index. Right, so we're shifting everything from the vector's container at this index down 1 element, or up 1 element, or right 1 element, or however you want to visualize memory. We're shifting it 1 element. One int-sized space forward in memory. There we go. That's the most generalizable way to say that. And now we have to specify one more thing, and we have to specify how much memory we want to move. Because remember, C isn't, it's not as smart as Java. It doesn't actually, store the sizes of our arrays or store how much space we have, so we have to tell it. And the amount that we need to shift is going to be our vector's container plus the size of the vector minus the specified index. Oh, what do you not like? To parameter of type unsigned int. Oh, right, sorry. It's not going to be vector container plus vector.size, just vector size minus index. And so, right, so we're saying we want to shift all of the things that come after index down in the vector. And so that is what this memmove line is doing. And now all we've got to do is insert our value. So we're going to say veccon at index equals value. And that is our insert function. It's relatively nice. And now we can optimize things if we really wanted. And we can say, well, okay, I mean, look, if we are trying to insert at the last index in the array, there's no real need to actually do the memmove. So I could say, if index is equal to vec size, or sorry, if it's not equal to vec size, then we're going to do this memmove, and you can do that. And oh yeah, we need to increment the vector size. But yeah, so now we've learned an additional tactic in C. If you'll remember in Java, we had a function called system.arrayCopy. It was really confusing, and it had this really awful signature that I always have to look up every single time I run the danger of using it. But what it did is it copied some values in memory. It copied some values in an array, which in Java is as close as we're really going to get to a C memory region. Memmove is basically the C equivalent of Java's system.arrayCopy. It's roughly the same thing. And so yeah, so there we go. There is our insert function. Let's go ahead and write some simple tests for insert. So the first thing we need to test is we need to insert into an empty array, or into an empty vector. So what I'm going to do is I'm going to call vector insert. I'm going to pass it my test vector. Oh, ampersand. What is it? And the value that I want to insert, let's just insert a 4 at index 0. Oh, but that needs to be the other way around. There we go. And I'm just going to assert that the size is now equal to 1. And that the value at index 0 is indeed 4. And so here we go. So now we're basically testing an edge case, right? Inserting into an empty vector. It's something that we don't do too frequently. You'd probably just call add, but we just want to make sure that the function works. And so let's go ahead and see. Great, there we go. That passed. Now let's say, okay, let's insert at the front of a vector. So now I'm going to add 2 elements to my vector. I'm just going to call vector add to my test vector. The values 5 and 7. And now I'm going to call vector insert into my vector. I cannot target keys today. And at index 0, I'm going to insert the value 3. And now let's have a series of assertions just to make sure that our list is still properly structured. It should have a size of 3. And our list should now read 3, 5, 5. Oh, sorry about that. 5, 7. Great, let's go ahead and run it. Oh no, and something didn't work now. What did we do wrong? Well, let us see. Oh, I forgot to change the indices. Right, I didn't write my test correctly. That'll do it. Oh, and we've still got something that isn't working. What did I do? Okay, so vector.get tvec 2 equals 7. Something went wrong. We've got some nonsense value instead of our 7. Okay, well, let's go see what happened. Well, let's see here. Let's make sure that we were actually copying the correct amount of memory. I don't think we were. So if we inserted an index 0, the size was 2. I am a bit of a dumb again. Remember that we need to multiply the amount of memory that we are shifting by the size of the values. So yeah, so we've got to multiply this size. Let me put this on another line so it's more readable. By the size of the data type that we have, right? So we're not just shifting this many bytes, vex size minus index. We're shifting that many ints. So we've got to specify size of int. And now if we run this, we've got it working. It's just me having a bit of a dumb. All right. So now what we're going to do is I'm actually going to be writing a lot of these functions that have a 3, a 5, and a 7, because we need to test inserting to the front, the middle, and the back. So I'm going to extract some of this logic now into what's called a parameterized test. And a parameterized test is basically a special type of test that has some common assertions that run, but different setup functions. And so what we're going to do here is we are going to write some different test cases that are going to feed into this single parameterized test. So the first one is going to be inserting into the front. The next one that we want to do, and here we'll even comment insert at front. We want to insert to the back of our array, right? So we're going to go ahead and start off by adding a 3 and a 5, and then we're going to add a 7 at the end of our list. So this is inserting at the back. All right, now we've got to do one more. Let's go ahead and insert in the middle. So a insert in middle. So we're going to insert a 3 and then a 7. And then we're going to add a 5 at index number 1. And so now that we've written these 3 cases, each time one of these cases executes, it's going to make sure that all of these assertions hold true. So let's go ahead and test it now. And there we go. We see that all of our tests have passed. And test.h is kind of convenient in that it shows us the line number that each of these parameterized tests occurred on. So there we go. So there's insert working. Now, while we are on the topic of moving memory, I would like to point out something that is really, really important. And that is that C actually has 2 functions for copying memory. There is one that's called memmove, and there is one that is called memcpy. These 2 functions do different things. They sound like they are almost saying, Prince Logic, you should start using this. It's a generalized unit testing framework. I'm going to open source it probably later today. Still working on it, but I'll definitely share it tomorrow if I release it on GitHub. But anyway, yeah, so we've got 2 functions that do memory copying. And if we actually go and we look at the man page for string.h, again, just to drill this into our head, how we can get help with C functions, if we look at man string, and then we go ahead and we look at memcpy, or memmove. Oh, is it really not in the documentation there? Okay, that's very strange. Well, oh well. Well, that's a shame. But anyway, if we look at man memmove, there we go. Then we can get help with copying memory areas. We'll see that in the description, it says, the memmove function copies n bytes from memory areas source to dest. Memory areas may overlap. Now, this is the important distinction between these 2 functions. We've got one function called memmove that will allow you to move regions of memory that could potentially overlap. And now for this function, for our list here, that turns out to be really, 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 really important. And let me explain why. Let's go ahead and pull up a quick drawing. And I'll show you why the fact that Memmove can move overlapping memory regions is so important. So, let's go ahead and get started. Oh, hello, can I please kindly get my window popping up? There we go. Okay, great. So, let's talk about moving memory. So let's talk about Memmove first. So let's say that I have an array. Let's say that we actually have our array that we're working with in test. So we're going to say that, let's just say, you know, we've got an integer array called test. And test is a fairly large array. It contains a good number of values. So let's go ahead and draw that here. Here we go. So here's test. All right, so test contains the following values. It contains the values 1, 2, 3, 4, 5, 6, and then 2 nulls. All right, and now let's say that I want to move this region of memory, 4, 5, and 6. So I want to move these bytes down 1 position. And so I'd really like to shift them down a single index. So shift 1 forward. And now the way that I'm going to do that with Memmove is exactly what we just talked about. So I'm going to call Memmove of test plus index 3, right? Because this is index 3, to test at index 4, which is this index. And of course, we've got to remember our destination comes first, so we're actually going to write test plus 4. Then our source, test plus 3. And then our size, which is, of course, going to be 3 elements times the size of int. All right, and let's see what happens when we run this Memmove call. So what Memmove is going to do is it's going to do the following. It is going to first initialize an auxiliary array. And so what it's going to do is it's going to say, I'm going to look at the number of elements that you are trying to move, and I'm going to initialize an array that is that many elements long. And so it's going to create an array, and we're just going to call this temp. And so we're moving 3 elements. So temp is going to be large enough to store, of course, 3 ints. Oh, that's wrong. There we go, 3 ints. And now what we are going to do is we are going to copy the values that you are trying to shift. So these values here are going to be copied into this temporary array that is allocated off somewhere else. And so we're going to copy these values here to 4, 5, and 6. And now after this has happened, then we are going to replace the values in your original array. And so it's then going to say, all right, we're now going to move the values in test. So let's see here, test had 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. There we go. And so the values at the beginning are obviously going to stay untouched. We're still going to have this 1, 2, and 3. And we're actually still going to keep this 4, right? Because we're shifting down 1 element. But now we're going to copy each of these values from temp into the new array. So we're going to copy this 4 down here. We're going to copy the 5 into the next element and do the same thing with the 6. And so these are our values that we have transplanted from our temporary array. Oh, that didn't work. That we have transplanted from our temporary array back into our destination. And that is how Memmove works. Memmove creates this auxiliary array before it does the copy. And now you might be asking, wait a second. Why? Why would it do that? Doesn't that seem like a waste of time to like create this auxiliary array and copy values and then copy them back? Why can't you just move the values directly? Like, why couldn't you do that? That seems like it would make a lot more sense. And the reason for that is that if you don't, you might end up accidentally overwriting values. And we can do that overwriting using another function called memcpy. And so let's go back here into vector, and let's just, for the sake of argument, let's actually now change our function from memmove to memcpy. So all we've done is change this. We've changed from memmove, which creates this auxiliary array, to memcpy, which doesn't. Memcpy just shifts our values. So let's go ahead and run our program now and see what happens. Well, everything passes, and that, yeah, I guess that makes sense. I guess it's because we're not doing anything that's too complicated. If I make this -1, will that trigger it? Ah, there we go. There we go. Great. Okay, cool. So you'll see here that if we do memcpy, well, I got an error and you couldn't see it. But anyway, what's happened is memcpy is trying to copy our values, but as it copies them, it is overwriting some of the values. And so let's go ahead and switch this back to memmove, and I'll show you what I mean. So memcpy does not create an auxiliary array, meaning that what memcpy is going to do is as follows. So let's go ahead and say, okay, so memcpy. Oh, let's make this black so it's a little bit easier to see. Well, actually, we'll recolor some of this just a tad, make it nicer to read. So this up here was memmove. And now this down here will be memcpy. memcpy. And memcpy takes the exact same arguments as memmove, which makes the functions look even more similar. Let's go ahead and copy that, paste that down here. Great. And so after executing this memcpy call, let's look at what happens to test. Move this up a little bit. We'll try and fit all of this on one page, just to make it a little bit easier to read for us. There we go, that looks good. So test after we execute memcpy will be modified as follows. So here is test after running memcpy. 3, 4, 5, 6, 7. There we go. Okay, so the initial values, again, are going to be unchanged, right? Anything that comes before the destination pointer is untouched. It's not going to be modified. And so anything that comes before test plus 4, we're not going to touch it. And so this 1, 2, 3, 4, it's going to stay exactly in the same place. However, what happens next can actually differ between platforms. Some platforms have a safe memcpy that will prevent you from shooting yourself in the foot, but some don't. And let's talk about the dumb ones. So what will happen is we have 2 indices. We've got a source index. Let's say that, this is our source, and this is our destination. Actually, let me write those below. So blue is source, red is destination. All right, so we're going to start off by just copying this 4, right? We're going to copy the source to the destination. And now we're going to shift both indices down by 1 position. So we're going to shift the source here, destination here. Copy source to destination. Okay, great. Shift both down one index. So we're going to copy source to destination. And, you know, the C compiler's happy with all this, and the runtime is happy with this. It's like, yeah, okay, I see what you're doing. Yeah, we're just copying some memory. That's cool. And now we've hit, you know, the maximum number of elements that we wanted to move, so we'll stop here. And, hey, that's what you asked for, right? Well, not really. I mean, yes, in that we called memcpy, but no in that we didn't want to do that, right? We wanted to actually copy the 4, 5, and 6. And so what happened is, because memcpy is trying to progressively move values without creating a temporary array, you might end up accidentally overwriting the values that you were trying to shift. This is something that we ran into in Java too, right? This isn't unique to C. We actually hit this issue when working with arrays in Java too. It's just that C gives you the additional kind of like foot gun, right? Thing you can shoot yourself in the foot with by just giving you a function that will do it. And so now if we go back and we look at the documentation for memcpy, right? So here was Memmove, here's memcpy, memcpy. Then we'll see that memcpy tells us the memory areas must not overlap. And indeed, it even tells us use Memmove if they do. It's saying, for the love of all that is holy, do not attempt to copy overlapping areas using memcpy, because if you do, it's undefined behavior. We don't know what's going to happen. And so the man page even tells us, hey, please don't do this. The C standard says, don't do this. You can use memcpy if the regions don't overlap. Memcpy is faster, right? Memcpy is going to be faster because it doesn't need to make a temporary array. However, if the regions might overlap, then for safety, use Memmove, which does create the temporary array, to avoid clobbering data as we're trying to copy it. So that's kind of the big difference between Memmove and memcpy, and it's something that, again, beginner C programmers get really confused by. Because usually memcpy is alphabetically first, and so they just use that one because they look up how to move memory in C, and they get memcpy because it's the first on the list alphabetically. They're like, cool, this will work, and they put it in their program. They're like, what happened to my values? Why are they all wrong? And so, yeah, that's why we might want to use Memmove instead. And so now Tuna asks a question in the chat, if we make a generic vector, what would be the parameter for size of? Yeah, that's a great question, and that's actually what we're going to do right now. So, you know, it's all well and good to have a vector that works with ints, right? It's cool to have an int vector. We oftentimes work with lists of integers, and, you know, we like having integer lists. They're really convenient. But sometimes we would like to store other stuff in a vector, right? We would actually like to store, you know, just different things inside of a vector. And so what we are going to do now, in the last few minutes we have today, is make this vector generic. And it's easier than it sounds. In Java, we had these things called generics, and they were awesome and cool, and we could do really whatever we wanted with generics. And it was all very simple and straightforward, and all you had to do was change int to E, and you were done, and the Java runtime handled all the other changes for you. The Java compiler and runtime handle all the changes for you. Not so in C. In C, if we want to make this generic, I mean, there are two things that we could do. I'll begin by showing you what a lot of C programmers will do, and what will happen sometimes if you want really good performance on your vector. So, I'm going to copy all of the I'm going to copy all the text in this file. I'm going to make a new file called vector_float.h, because I now want a vector of floats. I'm going to paste this in here. I'm going to replace all instances of int with float, and there we go. We now have a float vector. I'm not kidding. Like, this is roughly what we would do. And this is actually what some compilers do to implement generics. C++ does this to implement generics. It basically just copies your generic type into everywhere you use it and makes a new class called something different. So, you know, this would be, you know, instead of vector, we might call it vector_f. And there you go. We now have generics. Not really. That was dumb, right? And you don't want to do that for every type you write. That would very, very quickly become very, very frustrating if we had to do that. And so what we are going to do instead now is get rid of that file. And we are going to change this type here in vector from int pointer to void pointer. And now void is a return type in C, you'll remember, means that the function returns nothing. Void pointer basically means the opposite. Void pointer means that this pointer, this memory address, could point to a value of any type. We don't know what it points to. It's kind of just a generic pointer. It's a pointer to something, but we're not going to specify what that thing is. And so yeah, so there is our void pointer. And this is a really great way to do pointer polymorphism in C, where you can basically say, we've got a pointer to anything, and then you can cast this. But I'm looking into the future, and I know I'm going to have to do pointer math, right? We had to do pointer math to do things like Memmove. And so as a result, I'm not going to want to use void pointer because I can't actually do pointer arithmetic on void pointers. Pointer arithmetic on void pointers is not supported in C. You can't do it. If I try and say con plus 1, I'm going to get an error from the compiler. And so instead what I'm going to do is I'm going to change this to a char pointer, meaning that essentially pointer arithmetic is now going to work like standard arithmetic, right? Because the size of char is 1. And so if I add 1 to a char pointer, I get the next address in memory. And I'm going to do all of the other memory computations by hand. I'm going to do all of the pointer math myself. And now I do need to do one more thing here, which is in addition to storing the capacity, I also need to store the size of each element. And so this is the number of bytes each element occupies within the vector. And so yeah, one additional parameter we've got to add to make sure that we can fit anything in this vector and that when we resize, we know how big the thing that we're trying to resize is. And yeah, BlueJay got this, and Tuna, you kind of mentioned this earlier. So yeah, both of y'all predicted this change. So well done to both of y'all in the chat. Very good. And so now instead of just passing the initial capacity, I also need to specify the element size. So I need to say how big the things that we are working with are. And so I'm going to go into vector create, and we're just going to keep modifying stuff until the tests pass. Prince Logic, you can put different things in this vector. Yeah, you could. You could totally put different stuff in this vector if you wanted to. I mean, you've got access to this pointer. You can do whatever math on it you want. We are going to make the assumption, though, that every element in this pointer is element size long. And that's how we're going to do our pointer math, by assuming that everything that is in the vector is going to have this many bytes. So that's the abstraction that we're making. We're saying that this vector kind of contains homogeneous data and that each element is going to be the same size. But we're not going to enforce it. Yeah, I mean, you can't really enforce any of that stuff in C. Nothing's going to prevent someone from just mutilating this array if they wanted to. Right? It's C. You can do that. So let's go ahead now and start making test pass. So the first thing that we've got to do here is, well, we need to add our parameter, right? So size of t element size. And I need to set my element size parameter inside of my vector. And now instead of multiplying this capacity by size of int, we're just going to multiply it by element size to say that we can have any element in here that has that size. Great. And there's vector create done. So now if I go back into my tests, I'm just going to make a very simple change. I'm going to go up here and say that this is now going to be a vector that stores ints. A generic vector storing ints. BlueJay is C. In C is width the same as size. Yeah, pretty much. Width and size are basically interchangeable. We typically talk about width when we're talking about like integers and sometimes floats especially. But width and size, yeah, they're totally interchangeable. You can use either. It doesn't really matter. The one time that they will differ is when we've got something like our vector, right? Our vector has a size, which is a number of elements that is not equal to the width of this array. And so it may differ in some very limited cases, but by and large, yeah, you can use them interchangeably, and I don't think anyone's really going to chastise you for that. So now let's go ahead and see what happened with our tests. Oh, I still have an instance of this running. Okay. Let's go ahead and terminate that. There we go. Okay, let's run this again and see what happens. All of our tests passed. And that actually makes sense. Right? That makes sense because this was an int vector to start with. But, yeah, you know what? Let's modify some stuff. Let's actually now, instead of int, let's make it a short vector. Vector of shorts. Still a numeric type, but different numeric type with a different width. We've now got 2-byte integers instead of 4-byte. And if we run this, it's still going to work because our system is internally consistent. I haven't refactored a lot of this stuff to use the new element size, and so it is returning the correct values. But also, when we're trying to write this stuff, we're actually running off the edge of memory, which we don't want to do. And so let's try and fix some of these things. So the first thing I've got to do is fix vector try resize. Here we are doing size of int. This is a really, really straightforward change. Vec capacity times vec element size. Right? Not a big deal at all. All good. Okay, let's move on. Add. So add now is a little bit more tricky, right? It's a little bit more tricky because these are now, because these are now char pointers. And what's going to happen is if I just try to assign this value to this position in the array, we are going to run into an issue. And the issue, of course, that we are going to run into is that I'm trying to assign an int to a char, and so this int is going to be cast down to char, meaning that it might get truncated. And so that's not good, right? That's not good. And actually, I now need to modify this a little bit so that we're going to say that I now want to add, and instead of adding an int, we're going to pass a pointer to the thing that we want to add. So yeah, so we're now passing a pointer to any type to the thing that we want to add to our list. So this is void pointer. Right? Pointer to anything. We're not really sure what. Prince Logic, do you autosave or do you :W out of habit? Apparently IntelliJ does autosave, like when you switch windows and stuff. But I like :W, which is save in Vim almost constantly out of habit. Like, it's muscle memory at this point. Like, you do something that causes you to go out of the window, :W. Takes like 3 seconds, so it's not that big of a deal. Better safe than sorry. Yeah, exactly, XISZ. Yeah, exactly. You never know when autosave might not work, is what I tell myself while relying fully on this piece of software to continue working in order to run these lectures. Yeah. But anyway. Now, we're going to run into an issue, which is, again, I'm trying to assign now a void pointer to a char, which we can't do. So to assign this value, I am going to need to copy its memory into my array. So I'm going to copy what this pointer points to into my container. Okay, great. So what I'm going to say now is I'm going to say, great. So now we're going to memcpy. And note that I am now, showing you memcpy, right? We're going to use memcpy just to demonstrate that it works, but also I am constraining the interface of my vector to say that you must insert a pointer, or the thing that this pointer points to, right? The referent of this pointer must not overlap with my vector. So in other words, you can't try and add the vector to itself, which sounds like something that would be very straightforward, but you know people would try and do it if they could. So we're going to, we would note that in the documentation or something. We would say, hey, don't try and insert things that overlap. We don't support that. But we're going to use memcpy here because it's faster. Now the destination that we want to add it to is our vector container plus the offset. And so that's going to be the vector's size times the element size. And so this is the destination location. It's the vector's container, offset by size number of vector, or size number of element sized values. And so this is equivalent to doing a really complicated array access. The value we're going to copy is just value. That part's easy. And then the size, well, we're copying a single value, so it's probably going to be element size. Right? And this is now how we do our assignment for our generic vector. We can't rely on the size of our value, so we're going to use memcpy instead to copy to our destination location the value that was requested, right? And this takes a pointer to the thing that we want to add, so this is completely fine to pass this pointer, and then the size that we want to copy. Noting, of course, that this vector could contain pointers, right? We could have this vector store references, like in Java. It could just contain pointers to things. But we are actually writing this vector like the C++ vector, which actually emplaces values inside of it. And so we're actually putting these values directly into our memory region, into our array. All right, now that we've done all that, let's go back and fix things. So we've broken a large number of tests. More specifically, it's now going to be a little bit harder to add these values to our array. And in C, you can do this in C++. Yeah, we can't just take the memory address of a number, right? That's obviously not going to work. But what we can do, for simplicity, is we can say short A equals 4, B equals 3, C equals 7, and add the addresses of these variables as our pointers. Say we're going to add these values. And now this is, again, this is just one of those C things. This is just a restriction of C that, you know, we're going to have some small difficulties when working with pointers, right? Because a pointer has to point to a location in memory, and we can only get one of those by declaring a variable. So we have to declare variables for the things we're adding. You know, it's a little inconvenient, but hey, we just got like a generic vector. That's much more useful, in my opinion, than not having to declare a single variable. So I'm actually still on team generic in terms of just take the memory address. It's not that hard. Lovely. Okay, cool. This one's even easier. Memory address of I. We'll change it to short, just to be good. Okay, great. Still good to go. And then insert we haven't talked about yet. And I'm actually just going to go ahead and comment out insert. Because I think it's now just going to distract us. So let's go ahead and, yeah, let's just go ahead and comment that out. Hi, insert. Indiff. There we go. Great. Okay, cool. So let's go ahead and now test vector add and make sure that vector add is all functional. Oh, uh-oh. Vector add single element looks like it's got a little bit of a problem. In fact, actually, it's telling me that the test started, and then we ran into a problem. And the problem we ran into is that we passed memory address 4. I forgot to declare my value as a variable. Not a big deal. We'll pass a pointer to a memory location that contains a 4 instead of the address 4. And let's make sure that I didn't make that mistake anywhere else. Doesn't look like it. So now let's run our tests. Oh, and we get a failure. Oh no, what failure do we get? Oh, interesting. Let's see here. Okay, so vector add single element didn't work. We returned a 0. Now, why did we return a 0? Well, that is due to vector get. Vector get, you'll notice, is still returning int, which is something we're going to need to change. But also, vector get is accessing this char array. And so when we try to access index 0, we tried to access character 0, which happens to be 0 for this integer, right? It's not, we didn't get our 3 that we were expecting because we tried to access a char and return it as an int, which is not what we want to do at all. So let's modify vector get to be a little bit more accurate with how we're doing things now. And very simply, I'm just going to change this so that it returns a pointer. Yeah, vector get is now just going to return a pointer. And what that means is that the user can now use this pointer to either get or set values in the array, right? Because we can get values from pointers using the dereference operator, and we can assign values to memory addresses as well. And so yeah, this is now going to be not int, but void pointer vector get. And we again just need to do some very simple pointer math to actually get this working. This is just going to be return, and the address is going to be the container plus index times the element size. So again, some very simple pointer math. Con is a char pointer, so adding 1 to it will increment the memory address by 1. So we're adding to this the index times the size of each element, which is basically equivalent to doing that array access that we did earlier with an arbitrary sized type inside of our vector. So now I've got to change some stuff, right? I've got to go through and change this so that, okay, now we're actually dereferencing vector get. And what do you not like? Oh, right. And so vector get is now going to return a void pointer, which we cannot dereference. We can't do pointer math with void pointers. We can't dereference void pointers. But this is really easy. All I've got to do now is cast it. So we're saying, okay, I know this is a pointer to a short. So dereference it as a short pointer. And now our test adds single element. Some of them didn't pass. Oh, and add single element still did not pass. What did you not like? What did we do wrong? That's okay. Let's very quickly go through and debug this. Let's see here. Vector add. We incremented the size. Vector get gave me a pointer. Vector con plus the index times the element size. So that should be 0 plus the element size. Let's go ahead and debug this. Just make sure that we're not doing anything dumb here. Okay, here's our vector. Okay. So con contains a 4. Lovely. Okay, that's good. Let's see here. So that contains a 4, so let's go ahead and step through. Perils of live coding. Okay, great. And so, let's see here. What value did we get out of that function call? Well, we don't really know, but if we go into our run tab, then we'll see that it was the wrong value. Interesting. That's a little bit annoying. Oh, sorry, I'm sorry. No, add single element did pass. Oh, sorry, I can't read. Right, add single element did pass. I am incapable of doing the reading. That's okay. Anyway, okay, great. So that proves that this works. So I just need to make the same refactor for all of these remaining tests. There we go. There's that. Oh, got to do the same cast here. And now you might be thinking as I'm typing all of this, you're like, wow, that's annoying. Like, what? I have to cast every single pointer that I pull out of this? And yeah, you do. You do, actually, because you know what type is stored in the vector, and the vector doesn't. And fun fact, this is how Java used to work. So prior to Java 1.5, the Java language did not have generics at all. Java didn't have generics. And so anytime you wanted to make a generic data structure like ArrayList, its type internally was object. And every time you pulled a value out of that array list, it would return an object, meaning you would need to cast it to the type that you know is in the list before you could actually do anything with it, right? And so, yeah, this actually works the exact same as Java pre 1.5, where we don't have generics, we have to cast manually. And it is annoying, but hey, it's a limitation of the language. We do with it what we can. All right. Let's fix up our last few tests, and then we'll call it a day. Let's fix up insert. All right, so insert. Well, okay, so we know right off the bat that I'm gonna need to change a few things here. Let's just change the easy one first. Let's change these assertions. This is now gonna reference a short pointer. so that we can do our dereference. Let's see here. Do we have any other assert equals? We do. We've got one right there. So short pointer. Oops. There we go. Great. Okay. So now our assertion should work, but our code is not going to because we need to update some things. And what we need to update is, oh, well, first off, we need to change these guys, right? Our vector add lines will now not work, so we need to declare some shorts. A equals 3, B equals 5, C equals 7. Address of B, address of C. Gonna go ahead and just paste that into all of these to make life simpler. Address of A, address of C. And then this will be address of B, which is not currently in scope. No, sorry, not B, address of A, address of C. And now our add lines will work, but insert is still all wonky. Oh, and that should have been B, not C. There we go. So now we need to go and update vector insert. And what we're going to do with vector insert is we're just going to change it the same way that we changed vector add. Instead of taking an int, then take a void pointer, pointer to anything, pointer to an unknown type, and change this here to void pointer. Awesome. And now what we're going to do is, well, let's see if we even need to change anything, right? So first off, we're going to call resize. Resize we've already fixed. Oh, this memmove line. Okay, well, this isn't too bad now, right? This actually isn't the worst thing in the world. We just need to make sure to change this to vec element size, and we should be good. Well, not really. If we just do that, we're going to get a really pernicious bug that would be really hard to fix. That would probably leave me sitting here staring at my screen silently and drinking out of my Hoth ice bar cup for the next 15 minutes wondering what we did wrong. The issue is that the type of this pointer, the thing that con points to, is now no longer int, it is char. And so we need to remember to multiply these indices just as we have in all of our prior instances by the element size. Right? Pointer math on chars does no offsetting. And so we need to make sure that we are applying this multiplicative factor, the size of our elements, ourselves. And then, you know, this assignment here, this vet conna index, yeah, I don't feel like retyping that memcpy line, so there you go. All done. Great, there we go. So now the eagle-eyed viewers may, y'all in the chat may notice that this code is annoying. It's odd, it's clunky, it's terrible to work with, it's error-prone. We're having to do manual pointer math everywhere. And our tests, at least, should now probably pass. Oh, but they won't. Right, because I need to change insert. So this is address of A, address of C, address of B. But now, at least, if we compile it and we run the tests, we get a segfault for insert empty. Probably because in insert empty, I forgot to update, yep, a memory address. I call this value, and that should really be a short. There we go, but now if we run this, then we see some things fail, and I don't want to read the Windows output, so we are just going to do it in here, where I get nice colors, because that's the point of the day we're at. And let's see what happened. All right, vector insert, line 73. What happened? What happened? Let's see here. So, this pointer, accessing the 0th element, returned 5 when we were expecting 3. And then this one returned 7 when we were expecting 5. So it looks like we've got one of our old friends, the off by 1 error. And that's totally fine. Let's go and look. All right, so let's see what we did. All right, And now we get to read, of course, again, this lovely, beautiful code. So, destination is going to be, oh, it's probably something to do with this. I feel like it's something to do with this. So let's actually go ahead and place a breakpoint in our function where something went wrong, which is line 5. Oh, not line 5, sorry. Line 73. Oh, and I'm realizing now that y'all probably couldn't see the pretty color output. I probably forgot to change screens again, but yeah, here's the pretty color output. And so yeah, we can see that we were expecting 5, we got 3. That's not good. So let's see what happened. That's on line 73 is the test that failed there. So let's go to line 73. And now the really nice thing, again, about this testing library is that because it's all preprocessor macros, it's fully compatible with the debugger. And so I can just use the standard debugger. Skip over, add. Those I'm not too concerned with. If I look at my vector that I'm expecting to see in my container, yep, we've got a 5, then we've got a 7. Perfect. And let's step into insert and see what happened. All right, vector's not null. We shouldn't be trying to resize. And we're not, so that's good. All right, so we are not trying to insert at the end, so we're going to see what happens. We're going to call Memmove. And now what we are expecting to see is that if I add, let's see here, a few watches, if I add, let's see here, I don't really want to do that. But anyway, we should be moving this memory down. And now this memcpy, if we look at our vector, should be changing the first element to 3. And note that we're going to have a whole lesson on using the debugger. And so if this is just kind of magic at the moment, it's totally fine. Right? We don't quite need to know that yet. All right. So we had an issue. It looks like the returned, our memcpy didn't quite do what we wanted it to. Because our container still stores 5 at the first index instead of 3. Great. So that actually gives us a really, really nice tip as to what we can go look at. And just to make sure that our value is correct, I'm going to add an evaluation to make sure that that value is 3, and it is. Perfect. So we've honed in on our bug. We know where our bug is now. We know that our bug is in this memcpy line. Let's figure out what we're doing wrong. Let's see here. Destination, source, size. That's what we're expecting. Okay. Lovely, lovely, lovely. We're not incrementing the size anywhere, so we're not doing anything wrong with regards to that. Oh, right. I made a little bit of an error. An add, we were adding to the end of our list, and here we're adding at the index, not at the end. And so, yeah, this is a copy-paste error. It happens. It happens really frequently, actually. There's this kind of rule of software development that, what is it? I think it's after 4 copy-pastes, the chance that you have made an error in one of those copy-pastes becomes like astronomical, in addition to the fact that it's almost always the last copy-paste that is wrong. And so we've actually proved that rule here. I can't remember what that rule is called, but it's got a name. I'll look it up later. But yeah, so here we go. We've now got a fully functioning generic vector in C. And yeah, parts of it were annoying, right? Parts of it were admittedly annoying. This wasn't fun. We didn't like having to cast everything, but hey, you know what? We can just claim it's no worse than Java 1.5. Get over it. And this wasn't great either. We had to do pointer math, but we got through it. And so you might ask, well, okay, great. If we can write these generic containers for C, where are they, right? Like, I want to use these. Where are they? And, well, the answer is C programmers typically don't do this. C programmers actually typically shy away from these types of hyper-generic data structures. And there's 2 reasons for this. The first one is that, A, they suck to write. We just saw that. And B, this just isn't a typical pattern that C programmers use. They typically will pick other data structures or go with the kind of copy-paste approach that we saw earlier. And so yeah, so this is actually some very advanced C that we've written today. A lot of people don't ever write stuff like this. And so yeah, we've really made it into the big leagues now in terms of writing some pretty fancy code. But also, this isn't really, you know, the most idiomatic C way to do things. It's useful for us as Java programmers to have generics, but a lot of C programmers would look at this and go, hey, what are you doing? Don't do this. That's a lot of pointer math. That's like a lot of pointer math. Maybe we should reconsider. And so this brings us to choices of data structures. In Java, we used vectors, array lists, like all the time, right? They were basically free. It was really easy to make them. They had a really easy interface. With generics, they had an extremely easy interface. There was nothing too complicated about their use. They were great. We loved array lists, right? Array lists were great. In C, you're not going to see people use this type of data structure as much. Vectors are not a frequently used data structure in C programming. What you will see is arrays of a fixed size, because a lot of C programmers will just basically pre-compute the sizes of their arrays. They'll say, well, how big do I need this to be? Does it fit in memory? Yes. Jam it in, hard code it, done. Or they will use a linked list. Linked lists are used more in C than they are in Java, partially because it's a lot faster, and partially just because they're easy to write. They're really easy to write, right? Like, linked lists aren't hard. And more specifically, the type of linked list that is used is a type that's called an intrusive list. And that is what we're going to probably talk about tomorrow in preparation for the first assignment, which is going to be you writing a linked list in C. And now, this is going to be, it's a fairly straightforward assignment. It shouldn't take you too long. And I'm just going to give you unit tests. Like, I'm going to give you all of the tests. And so, like, if you pass all the tests, then your code works and you're done. But we're going to talk about intrusive data structures tomorrow. It's a new type of data structure that's used a lot in C and never in Java. So yeah, intrusive data structures. And we'll talk about the trade-offs, right? We learned that linked lists are slow because you have to traverse through them to access things. And in C, they're even slower because it turns out that your processor is very, very good at accessing data that is right next to each other, because of something called caching, a behavior called caching. That is not what we're going to talk about here in this stream or in this series, because this isn't a full comp arc class, contrary to what it seems like at this point. Yeah, so we're not going to be talking about caching or locality or any of that, but just know that arrays are typically faster than linked lists. It's just something that we already know. But yeah, so we're going to talk about linked lists in the future. And so yeah, that is really the end of today's lesson. So I will go ahead and leave this code up as I prepare to upload the notes. If anyone, as usual, has any questions, please feel free to type them in the chat, and I'll be more than happy to answer them. And again, I'll be happy to, if there's, you know, a little bit of the code that you want to see again, I'll be happy to scroll through it. Or I can very quickly post this to GitHub as a gist. Maybe we'll do that instead. But yeah, let me know if you've got any questions. More than happy to answer. But for now, I'm just going to be uploading some stuff. Okay, Prince Logic says, yes, please. Yeah, sure. We'll put the vector code up. Yeah, we'll put the vector code up. Yeah, it could actually be really fun to play with. So yeah, I'll put up the vector code. I'll also put up the test file. So if you want to make sure that, you know, if you're just playing with it and you want to make sure you didn't break anything, then you can totally do that. Yeah, I'm more than happy to put it up on GitHub. So yeah, I'll do that. But yeah, right now I'll just sit here and wait for some questions as we listen to some nice Beethoven. That's been our music of choice for the day. We listened to sonatas. What did we do? We did 3, 4, 5. No, we didn't do 3. Sorry, we did 4, 5, 7, and 9 are the Beethoven sonatas we've listened to today. Very nice music. We're in the 9th symphony right now. This is the third movement. Yeah. So almost through it, actually. But yeah, let's go ahead and upload the notes. Any questions, feel free to post them. And let's see here. This is part 5. Part 5. Upload it to C for Java programmers. There we go. All right, let me get you a link to our notes. That's the first thing we'll do here. Let's see here, drive. All right, great. So here are our notes for the day. Here's our notes PDF. The only thing we added today was that info on memmove versus memcpy and how they work, but that can actually be kind of useful to have. So yeah, go ahead and you can play around with those. And now for the code, let me make a GitHub gist for you. So this is going to be a very simple generic vector in C with unit tests. All right, so let's do vector.h will be our header file. Yank that, paste that. Oh, right. Copy is plain text. It's 4 spaces, no line wrapping. Add another file, vector.c. Do the same thing. Copy is plain text. There we go. Now we'll add test.c. And we'll go ahead and add, oh, that's the wrong file. Edit, copy as plain text. There we go. And then the behemoth that is test.h. Let's go ahead and add that. Let's make sure no one's posted anything in the chat. I'm not really watching it. Nope, we're still good. All right. And here is test.h. So yeah, as I mentioned earlier, test.h is actually going to be its own GitHub repo soon. I actually already have a repo called test.h, but it's an old version. It's an old version that didn't work on Windows. Yeah, so I had an older version that didn't work on Windows because I thought that it wasn't possible to get it working. And then I did some research into Windows executables and played around with Microsoft C compiler, and it now works all the way back to Windows 95. So yeah, so that's the version that I'm giving you in this GitHub gist, and that will be going up on GitHub later today, and I'll give a general repo link tomorrow in case anyone just wants to use this in a project. But yeah, we're going to go ahead and make a public gist written for the tutorial series C4 Java programmers. All right, we'll make a public gist so that everyone has access to it. All right, here you go. Let's see here. And I'll show you how to access this in case you want to play with it yourself. So let's go ahead and pull this up. And we'll project it. So here is here's the GitHub repo. And here, let me send you the gist. So this is code from today. There we go. All right, and so this this gist contains 4 files. It contains test.c, which is the tester file that we wrote, and all of our tests. It contained test.h, which is the pre-release version of test.h. I just ask that y'all don't release this part, because again, it is GPL3 licensed, and so we don't want to break my license, so just keep it here in the GitHub repo. And then we've got vector.c, which is our implementation, and then of course vector.h, our header file. You're more than welcome to play around with this. I'm just going to say that everything but test.h is WTFPL, which stands for the whatever the F you want public license. Literally just means you can use it for anything. I don't care. And test.h is GPL3, so it's free and open source. But yeah. There you go. There's all the code. Y'all are more than welcome to play with it and do whatever you want with it. And if you want to do that, then what you can do is just go up to the top of this GitHub gist and just click download zip. And that will give you all of the files in a zip archive, so you can just unzip them to a directory, compile them yourself. Super duper easy. If you're on Windows, you can just import these into Visual Studio. And if you are on Linux, then again, the way that we're going to compile these is we need to make sure that we include both test.c and vector.c in our compile, and we'll type the name of the binary. And you'll get some warnings. You will get some warnings about some of this stuff, and that's just because of printf format strings. You're completely safe to ignore them. They don't really mean anything. They're just printf warnings. Yeah, not a big deal at all. Print logic, yeah, you could do star.c. Right, so let me show you. So the star is a convenience provided to us by our shell. It's called a wildcard. It means expand to everything that matches this pattern. So this will expand to everything.c. And so if you have this in its own file, right, and so if you have, or sorry, in its own directory, then you'll be good. And so if you just copy all this stuff into its own directory, then you'll have no issues. Those will be the only C files there. But if you have these C files in a folder in which you have other C files, then you could end up compiling things you don't want by using this wildcard. So yeah, I would recommend, just using the command, cc test.c, vector.c, and then, -o your output binary. That's how I would compile this for now. And you can use star.c if you've got it in its own folder, but just for safety, let's just say we'll type in the file names manually, which is typically what you'll want to do. Alrighty. And with that, I am going to head out. I hope that everyone enjoyed today's lesson. We did something that's pretty cool. We wrote a full data structure, repackageable as a reusable library that other people can use given the header file. And we wrote some unit tests. We learned about how to do unit testing in C. We saw my weird jank unit testing library that exploits dark magic of ELF and PE to run tests automatically. And you got to see me debug some code, and I didn't know, I hadn't pre-planned the debugging. So yeah, you got to see my actual debugging process. So yeah, I hope everyone enjoyed today. We're going to be back at noon Central Time tomorrow to do some other stuff. We're probably going to be talking about linked lists, and we're going to be talking about intrusive linked lists, in addition to covering one more feature of C that we want to learn. And we're in the home stretch in terms of learning about, like, the base language. We have, like, one more concept to cover. It's called unions. And they're pretty cool. And then after that, we're going to be talking about some other fun things. We're into the next week. We're going to be talking about how floats work. Ever wondered why when you add 0.1 and 0.2 you get 0.300000001? Yeah, we're going to talk about that. We're going to talk about debugging your C programs using GDB and Valgrind. We are going to talk about performance profiling, all kinds of other fun stuff. So yeah, stay tuned for that, and I hope that everyone has a great day. See you at noon tomorrow. Take care.